Okay, so let me make some announcements. I'm just going to write them here. Ashish will send out some announcements through the Triton Ed, but just so we have it. So tomorrow, Tuesday, there's going to be a MATLAB session from 4 to 5 p.m. In room SME. Ashish, what room is it? 347. Okay. So that's for anyone who wants extra help with MATLAB. And then TA office hours. There's going to be one Wednesdays, 9:30 to 10:30. So that's before this lecture. Room TBD. But Ashish will send out an email. Okay. And then there was the next office hour was Thursday 4 to 5. So this will be Ashish's office hours, and this will be Sean's. Now I think there was a mix-up that Ashish was just telling me that this wasn't necessarily on the poll. So if these two times don't work out for you, and there's enough people who need enough of their time, send email to Ashish and Sean, and we can do another iteration. But that's it, at least for this week. So both those office hours are before the due date, the homework due date. All right, so are there any questions on that? Okay, so before we get started, are there any questions from last time that people would like clarifications on? Okay, so today what we're going to do is the goal is to finish up the X-ray imaging equation. So this week is certainly going to be a lot of sort of background theory. Some of it's familiar to some of you, others it will be new to you. The idea is we're just going to sort of, if you've seen it before, then just relax and try to sort of see how it's being applied. If it's new to you, don't worry. We sort of will cover the topics again in the homeworks, in review sessions, and really what you're really responsible for in terms of the quizzes is really material that's covered on the homeworks. And any of the sort of the previous quizzes in terms of example problems. That's what we're looking for. There's a lot of material that's covered in this course, but really what you want to do is we'll try to emphasize what are the key concepts that we would like you to get. All right? So the first slide I'm doing is a slide we went over last Wednesday, and there was actually a mistake that I want to point out. So we're going to go over this again. So this is basically just showing that if I have a very simple image with quantities A, B, C, and D, and I define my coordinates as M and N, okay, that I can write that as a weighted sum of Kronecker delta functions. Okay, so the coordinates we'll define. So this is, let's say this is at 0, 0, 0, 1, 1, 0, and 1, 1. So those are the coordinate systems. All right. So I have at location 0, 0, I have a weighting of A times the Kronecker located at the origin. Okay, so that's this part. For this B, the Kronecker in the M domain is at the origin, so it's just M. And then in the N domain, it is, oh, sorry. Let's see, already got it wrong. Okay, it's, already got this wrong. Okay, so let's fix that. Sorry. So this is 1, 0, and this is 0, 1. Okay, so if anyone was confused by what I wrote, that's because it was wrong. Okay, so so this is just showing that you need to check your work. So luckily, as I was doing this, I realized it was wrong. So this is going to be shifted by 1. It's 1 away from the origin, so it's M minus 1, N, okay, plus C delta. This is in the M domain, it's at the origin, so it's M. But in the N domain, it's shifted up by 1, so it's N minus 1, plus D times delta. And this is shifted in both ways, M minus 1 and N minus 1. Okay? So in fact, this is now correct. So these were incorrect in lecture 2, but this is now corrected. Okay, so use this version if you're studying or reviewing. All right, any questions on that? Okay, so as we discussed last time, the Kronecker delta is easy because it's very simple. It's either 0 or 1, and it's defined on discrete coordinates, so it's pretty easy to understand. Let's see if we can get this off. Okay. Maybe that'll disappear. Okay, good. All right, so what we're going to actually do for our objects, though, is because we need something continuous, we're going to spend a little time talking about Dirac Delta function. Now, some of you have already seen this. It may be new to some of you. It's used a lot in math and physics and engineering, so it's a very useful thing to know if you haven't covered it before. The notation is the only difference in the notation is we're using parentheses instead of brackets. So we can have a 1D Dirac Delta function. We can have a 2D Dirac Delta function, where if you want to be really sort of a stickler, you could put a little 2 on there, but we'll just simply write it as delta xy because it's understood. It's a 2-dimensional. We could have 3-dimensional, and in general, you can have n-dimensional, if you want to do like string theory or something like that. Okay. Okay, so the definition of the delta function is pretty weird. It is equal to 0 when x is not equal to 0. So it's basically 0 everywhere, okay? And yet it has an area of 1, all right? So basically it doesn't exist. It's not an ordinary function because, and it's what's called a generalized function in that you can't really define what its value is at any given point. You can only define what its area is and what it does to other functions, all right? But in terms of interpreting what it means, we can think of starting off with, for example, this is like here we have a rect function, right? So this is just rect of x, right? It goes from -1/2 to 1/2 and has a height of 1, right? So that has an area equal to 1, all right? Now we can imagine taking a rect function as follows. We could take rect of x over tau and multiply it by 1 over tau, and see what happens as tau goes to 0. Okay? So as tau goes to 0, this quantity, basically, it's going to remember this is the width of my rect function, right, in the denominator. So that's this width tau. So as that width shrinks, okay, what we're saying is we're going to let the height go up. So as 1 over tau is going to increase, such that the area of each of these rect functions is still 1. So area of 1, and this also has an area of 1. Okay? So one way you can think of the Dirac Delta function is simply the limit of all these rect functions as the width goes to 0 and the height goes to infinity. Okay? So where do we use the delta functions? Well, here's one place where we use it, where this is what we talked about last time, where we have some source function, s of x, and we have a transmission function. So this is how many x-rays are getting through, okay? And so we're saying in this case, it's basically represented by this delta function with some scaling factor, but the important thing, it's a delta function located at the location x0. So it's 0 everywhere except at that location x0. So that's a pinhole. That's what we use to represent an ideal pinhole object at x0. Okay? And so we said if we did that, then our source image would simply be our initial source, but it's going to be shifted by mx0, where this is the object magnification. Okay? And then the source itself is scaled by the source magnification. And then there's also this scaling factor that's related to the source. This should actually have an absolute value sign on it. Okay? So let's do an example of that. So here's an example that might help you with one of the homework problems in terms of just sort of seeing how the math is fairly straightforward. I would say a lot of the problems in the book are, the problems we'll assign you are, they may look somewhat scary, but they're actually fairly straightforward. So as long as you're just willing to dive into them, you should be fine. So let's look at this in a little more detail. Okay, so let's assume, so we have our function s of x, okay? And it's just going to be some Gaussian, right? So this is my e to the minus x squared over 2, okay? And I want to say what, and I'm going to have as my object, it's a pinhole, okay? Located at x naught, okay? So all I want to do now is plug in to my expression. So I know that my image, or in this case what I'm calling my impulse response, is just given by this equation here. It's going to be a shifted and scaled version of my source. All right. So all I need to do is, all this says is, wherever you had x, replace it by x minus mx naught over m. That's all that's saying, right? So I just take this, and wherever I had an x here, I just replace it with that. And I'm done. Basically, that's all I have to do. Okay. So this is now my impulse response for any x naught and any m and any, so the variables are x naught, m, and little m. Okay? And so typically in most problems you have to figure out m and m. You might be given an exact value for x naught, or you might just, it might just be left as a variable. Okay? So really there's not too many degrees of freedom here, so let's just do a specific example and then draw what this shifted source looks like. All right? So let's say we take z equals d over 4. Then little m, the source magnification is just going to be given by this equation, which gives you minus 3 once you plug it in. The object magnification is d over z, which equals 4. And as a sanity check, remember we said that little m equals 1 minus big M, and that's 1 minus 4 equals minus 3. So you can always check your answer. All right? So now what we do is, all we do is we plug in these values for m and m into this equation here. So we have 1 over 3 here, okay? There's a 3 here because we can drop the minus sign because it's squared anyways, so that's fine. We have the 4 coming in here, and that's all we did, okay? So now we just plot what this looks like. So is this going to be fatter or narrower than the source? So this, let's say this has some width of, I don't know, W. What's the new width going to be? Is it going to be less than W or bigger than W? Bigger, right? Okay, so basically we know that it's going to look something like this, and its height is going to be, where this height was 1, this is going to be 1/3. Okay, and now that's if it wasn't shifted, right? So what we have isn't quite correct, right? So this is if it wasn't shifted at all. What we actually want is a shifted version, so we have to shift it by 4x naught, and you're not given x naught, so you can just put it anywhere you want, and it will basically be a shifted version. Okay, so there's a shift and there's a scaling. Okay, so that's sort of basically just showing you how you work with this equation. All right, any questions? Okay, so this is the answer here. All right. Okay, so now because we're dealing with images, we also have to deal with two-dimensional Dirac Delta functions. And they're defined sort of with the 2D extension. So we have delta x equals 0 whenever x squared plus y squared is not equal to 0. So basically everywhere except the origin, it's 0. All right? And yet the area of the function is 1. Okay? And so we can play the same trick. We can think of these little sort of cubes. So that this is like the width w. So let's say this has width w and w. Okay, then to make this unit area, the height has to be 1 over w squared. Okay, in this case tau. So let's say this equals tau. Okay, so either tau goes to 0 or w goes to 0. It doesn't really matter what notation we use. So it's the same picture. As this width is getting smaller, the height's getting bigger, such that it ends up being just a spike at the origin. All right, so that's the 2D Dirac Delta function. The example of this is what happens when we talked about before, we have a source, and here's our detector. We talked about what happens when we have a pinhole object, and so this is our object. What happens when we move it right up next to the detector? Okay, and so now we're going to give the sort of the formal definition of what happens to that. So basically, it turns out that we know that sort of in general, we've already said that wherever I am, we're going to have a magnified image of my source. Okay, so if I have any source and I have any pinhole, okay, so the rays are going to go through and somehow hit. And the idea is no matter where I move this location, this Z location, okay, all the rays can somehow have a path through that hole. Okay, so whatever is the image, if I integrate over it, that area should be the same. Okay, so it's basically, and so the book goes through this. I'm not going to go through this in detail, but by doing this, you can sort of figure out that that leading constant has to be related to 1 over m squared. Okay, and so what it means is that our image is going to be related to, is basically this thing here. It's a scaled version of the source divided by m squared. Okay, and this is very similar to what we just went over here in the sense that if we think about any source in 2D, say x, y, and it having some height, that's its value, as this m basically is shrinking, so that m is sort of like this distance here, and I have 2 of those, so I have m and m, okay, that's my base, the 2 dimensions of my base, right, so that's shrinking, right, and then my height here is 1 over m squared, and so that's getting bigger, okay, so this is the same thing. As I move my object closer to the detector, the width of it is shrinking, but the intensity of it's increasing, and that becomes a delta function. All right. So that's just showing you that this is how we represent things using the delta function. Okay. Now, once again, it's an idealized object. You're never going to be at d equals 0 because there's always going to be some finite width. So we're just using this because it's very useful to have idealized objects to say what happens in the ideal case, and then we can always back off and say what actually happens in reality. Right? So I'm going to talk a little bit about generalized functions. This is, you can sort of think of this as more philosophy or anything. I mean, you're not responsible for this, but I think it's good to have some background. So Dirac Delta functions are not ordinary functions. They're not defined by their value at each point because we don't have a value defined at 0. Okay. Instead, they're what we call generalized functions, and they're defined by what they do underneath an integral. Okay, and that's going to be important. Now, we're just going to spend a few slides talking about this. I mean, there are whole books written about this, so if you're really into math, you can go to the library and get a whole book about generalized functions. Okay, so we're just going to give you enough so you can understand how to work with them. So the most important property of the Dirac Delta function is its sifting property. Okay, and we're going to see this when we look at sampling. And basically what it means is if I take a Dirac delta, a shifted one, say delta x minus x naught, and I multiply it versus some function g of x, where I assume g of x is fairly smooth, it's actually going to pick out the value at x naught. And so it's saying that the value of this function is g of x naught. Okay? So you can think of it as like if I had some function g of x that's varying smoothly, if I multiply it by something like this, and then I look at the area under this, okay, as things get really small, it's really just going to pick out the value at g of x naught. So it's a really useful function for sampling. It's saying, I just want to know the value of the function at some location. All you have to do is use the delta function, and that's how we're going to represent sampling. All right? So we'll see this again, but today we're just introducing this notation. So what that means is, in the Kronecker delta function it was really easy. We could just represent all functions as scaled versions of shifted Kronecker delta functions, and that was very simple to do. And so this would be like just to be a summation of, say, g of m delta, m minus k, something like that. Okay, so that was easy because we could use summation signs. Everything's well defined. For Dirac delta, the same intuition applies, but you sort of have to take it on faith unless you want to go into all the really sort of complex, sort of the deep details. So what we're just saying is that, intuitively, if we imagine delta x being really small, then we could represent any function. Like you go back to calculus, you can represent any function as just all these little small all these small rectangles, like Simpson's rule or something like that. Okay, and so you just imagine as those rectangles get infinitely small in width, they become delta functions. And so in the limit, instead of rectangles, we would represent, you could imagine just a bunch of little delta functions representing any object. Okay? So the claim we're going to make is any function can be represented by delta functions. Okay? But we use integrals because the spacing between those delta functions goes to 0. So everything is now in the limit. All right? So we're not going to really talk about, get into all those limits here. Just for this class, just realize that this is the intuitive picture, and just know that theoretically you can actually extend it to integrals and delta functions. All right? We can do the same thing with a 2D function. You can imagine it representing any 2D function as just a bunch of these rectangles with height. Okay? And then in the limit, obviously, it's just going to be a bunch of delta functions with, and I can't draw infinitesimal spacing here, but just imagine that these are going to be, as the spacing gets closer and closer, they become delta functions. All right? So basically the idea is we can represent any function here as shifted delta functions multiplied by some weight. All right? So it's the same intuition we had for Kronecker delta. It's always going to be any function is a bunch of shifted and weighted delta functions. All right? Okay, and then one last useful fact before we sort of get into some more sort of simple concepts is one really useful thing is that sort of, it looks weird when you first see it, but any scaled delta function is just equal to the delta function multiplied by the scaling term. Okay, so for example, delta AX just equals 1 over magnitude of A delta X. All right, so that means that delta AX actually acts like delta X multiplied by 1 over A. Okay, and just to go through it, imagine I took delta AX and multiplied by g of x and integrated. Okay, then I could do substitution of variables. I could say, well, u equals AX, therefore du equals A dx. And so I can have, this is delta of u, g of u over A, d of u over A by substitution of variables. Okay. And I'm going to assume A is less than 0. You can do for A greater than 0 here. If you do A less than 0, then you just get the minus sign, which gives you the absolute value. But we'll just go through this one here. So I can pull out the 1 over A, and then I have delta of u, g of u of A, du. Okay? And now we can apply the sifting property. Remember, this is just going to pick out the value of g at when u equals 0. Okay, so this scaling factor has no effect because 0 over A is just still 0. So this is just equal to 1 over A g of 0. So it acts exactly like a delta function, but I end up multiplying by this factor. Okay, so that's just something that you might, when you're seeing scaled delta functions and all of a sudden they end up like this, that's why they look like that, because there's this identity. All right? So that's a lot of background. Now we're gonna sort of shift back to some simpler concepts and then sort of take all this stuff and put it back together and come up with the X-ray imaging equation. Okay. So before I go on, are there any questions? Okay. So we've talked about the impulse response before, and so the definition is we might have some impulse in our object domain or our source domain with maybe some coordinates zeta and eta. And then we imagine measuring it somewhere else, our impulse response here. And so it depends on where the input was. So that's where my input was. And now I'm actually measuring it in some other output coordinate system. Okay? So you can imagine my object's here with some coordinate system, and I'm measuring it somewhere else in another set of coordinate systems. Okay? So we want to look at what are the things that can make our life easier when we look at impulse responses and why the impulse response is super useful to characterize. And so that throughout the course, if we know what the impulse response is, then we know how well the system works. Okay? So the first concept we're going to review or go over for the first time is linearity. So it's fairly simple. If I have an object I of 1 and I look at it through some system R, let's say my output is k sub 1. Okay? I take another one I sub 2, I put it through that same system, and my output is k sub 2. Now, if by the addition, so linearity has two properties. One is addition. So here, my input is I1 plus I2. Okay? So if this system is linear, then the output should be k1 plus k2. Okay? So the the response to any sum of inputs should just be the sum of the outputs. So that's all it means. Okay. And then the second property of linearity is scaling. So if I have I1 and I pass it through and I get K1, now if I multiply by some scalar A1, like this 2 or 3, then my output should be scaled by the same amount. Okay? So that means the response to a scaled input is simply a scaled output. So that's all that means. Okay? So this is just how we write it, the notation. This is my system. I put in some, these are my scaling factors. I'm adding these two together. And if the system is linear, then I'm going to have A1, K1 plus A2, K2. And that's it. There's nothing more complicated about this. All right? So any questions on that? Okay. So then let's do some questions. We're not going to do all of these questions, but let's do a few. Yeah, actually, let's have you guys do this one, part A. So the question is this a linear system? All right, so I'm going to set up the poll. Feel free to discuss this with your neighbor or whoever you'd like to talk to. Let me get the poll ready. Okay, so okay, everyone had a chance to respond? Looks like most people responded. Okay, so you can keep entering your responses, but just to tell you what the polling results are so far. So we have true or false for this one. And right now we are standing at 78% true, 22% false. Okay? So does anyone want to change their vote? Now it's 82%, or 80 and 20. Okay. So basically it's converged to 4 to 1 people think that it's true, that the system is linear. Okay? So let's take a look at whether it actually is linear or not. Okay. So the system says put in G, add 10, the output's G plus 10. That looks pretty linear, right? So intuitively, yeah, that's linear. Okay. But let's actually go by the definition. Okay. So if I do G, it gives me G plus 10, right? Okay. If I put in an H, let's say, it's going to give me H plus 10, right? What happens if I put in G plus H? What does the system give me by definition? G plus H plus 10. Okay, is that equal to the sum of the other outputs? Okay, so these together give me G plus H plus 20, so these are not equal. Okay, so according to that, is the system linear? No, so the system is not linear. So this is a favorite quals question that professors love to ask, right? Because most people get it wrong. Okay, so just so you know that if you ever have this question, that things that seem linear, by strictly speaking, aren't always linear. Okay, so just go by the definition. Any questions on that? Yes, question.
Written like this, is the 10 assumed to be part of the operation as opposed to like a second function that's being input into it?
Yes, that's right. This is considered your black box.
Oh, okay.
Yeah. That's a good point. Right. If it was just addition, then it would be fine. But that's considered to be your system. Okay. So let's do one more thing. This is actually a very useful one. We're going to do C. Okay. So let's look at this. Here my input is g of x, y, and now my system. So this is my system here. Okay. It's going to move up by 1 and move right by 1. So it's going to give me gx minus 1, y minus 1. And the question is that a linear system? So let me open up that poll. Okay, so that should be open now. Okay, so this is a little more, people seem a little more certain on this. So 88% true and 12% false. Okay, so let's hope we're right. Now it's going to, dropping down to 80. Oh no, okay, it's holding still. All right, so let's look at this. Okay, so once again, let's just go to the definition. So I put in G and I get in this shifted version of G. Okay, now let's say I have some other thing that I put in. Let's say, let's call this, so this is, let's call this block G and let's call this block H. Okay, so now H is going to be shifted up by 1 and over by 1. So H is going to end up like that, right? Okay. And now, so G goes to this, H goes to a shifted version of itself. And now if I put in the combined G and H together, that whole thing will be shifted over, which will look exactly like that. Okay, so it is a linear system. Okay, which is good because we do a lot of translations in images. You move things around in images. So if it wasn't linear, our lives would be really complicated. Okay, so translation is a linear system. Is there a hand there?
Yeah, could you briefly explain how scaling would work in system C?
Sure. So let's say I multiplied this by 2 of G, right? Then the whole thing would just, this whole thing is just moved over. So the 2 would just change the color of that. Let's say it's a grayscale. Okay, so multiplying an image, like, if you look at, you could say its intensity would change. And so one way of looking at it is if I just change like how dark that blue is, it doesn't really, and I shift it, it doesn't really matter. Okay. The other way I could think about it is I could think about drawing it, in 3D, and then shifting it over like that, right? And then as I increase this height, it doesn't really matter because the whole thing still gets moved over. Okay. So I mean, it's sometimes useful to think about things in 3D like that, but it's just hard to draw, and I'm not a very good artist, so it's much better. I mean, and we look at images anyways, and so it is useful to start thinking about the brightness, either the blackness or whiteness of the value, or the depth of the color is giving you the sense of the value. Okay. Any questions on that? Okay. So now we're going to talk about superposition. So the first main concept we need today is superposition, which probably, has anyone not heard of superposition in like physics or anything? Okay, great. So we can sort of assume you know it, so we're just reviewing it, okay? So here's the idea. I can take any function g of m, and as we talked before, I can expand it as weighted and shifted Kronecker deltas, okay? So this is weighted. So this is the sum of weighted and shifted delta functions. Okay? And now let's assume I have some impulse response. And in this case, the impulse, so this is located at k. So this is something like at k. Okay? So delta m minus k is located, is a Kronecker at k. It's saying if I have a Kronecker delta function at k, the impulse response in response to something at k measured in the output coordinates m prime is just defined with this notation, h m prime comma k. So that's just the notation we're going to use. And now I want to know what is the response of my system if I know my impulse response. And in here, we're assuming that the impulse response may change depending on where k is. Okay, so we have to keep all this notation. So then what we're going to say is that I want to know the response of my system, and the L is telling me it's a linear system. Okay, so I'll use L to denote a linear system. And so we can say this is equal to L of G0 delta M plus G1 delta M minus 1 plus G of 2 delta of M minus 2. Okay, so we can expand our input as a sum of weighted and scaled. And now the first thing we can do by linearity is we can just use addition property, right? This just equals L of G0 delta of M plus L of G1 delta M minus 1 plus L of G of 2 delta M minus 2. Okay? And now we can also use a scaling property. This just equals G of 0 L of delta of M plus G1 L of delta of M minus 1 plus G of 2 L of delta of M minus 2. Okay? And now each of these terms was defined here. Okay? So that's equal to G of 0, H of M prime. The coordinate here, the value here is delta M minus 0, right? We're looking for M minus K, so this is delta M minus 0. So that's just HM prime 0 plus G of 1, H of M prime 1 plus G of 2, H of M prime 2. Okay? So it's saying if superposition holds, as long as I know the impulse responses, then I can just write the output without having to, as long as I know what the input is and I know that all the impulse responses, I can tell you what the output is. Okay? And then I can write this in this compact notation with the summation symbol. All right. So fairly straightforward, but just here we've used addition property, here we've used a scaling property, and so that's just showing how we apply linearity. Any questions? Okay, so this is the clean version. So if you can't read my handwriting, this is the clean version. Okay? And this is the, if we extend this to 2 dimensions and allow for delta functions and continuous. So now this is the extension to 2D and continuous. So here I have a 2-dimensional weight and these 2-dimensional Dirac Delta functions. Okay. Now I've got this integral sign instead of summation signs, but the overall answers is still the same. My output is just going to be now this double integral. I've got these weights here, and I have all these 2-dimensional impulse responses. So the structure is exactly the same, and so that's sort of the intuition is still the same. It's basically a weighted sum of your impulse responses. Okay. So let's do an example of that. In this case here, where we're looking, so this will give us a little more experience with our X-ray imaging equation. Okay. So here we assume Z equals D over 2. Okay. So what does little m equal here? It's equal to what? Go ahead. 1, yeah, or minus 1. Okay. And what is big M equal to here? 2, right? Okay, it's just D over Z. Okay, so we always, for these things, you always just want to write those down as something that's easy to figure out. So especially on a test, you feel a little better about yourself, right? And also you need to use it. Okay. So and then we know that my input is S of X equals rect of what? X over what? X over 10, right? Okay. And then I know my output is basically given by 1 over m. For any impulse, it's going to given by S of X minus big M X naught over m. Right? And I have to do that for each impulse. Okay? So this is my input, right? It's a bunch of, it's 2 shifted, so this is like delta of X plus delta of X minus 2.5. Okay, so it's 2 shifted, it's 1 Dirac delta and then a shifted 1. Okay, so now I've already created a slightly more complicated function. So this first impulse, there's no shift, right? Here, for this one, the x naught is equal to 0, right? We haven't shifted. So we know that the response to that is simply going to give me, it's going to be this, right? It's going to be 1 over 1, which is 1, rect of x minus mx naught over m. So it's m is equal to 1, so it's the same, the source is the same. X naught is equal to 0, so there's no shift. So I'm just going to have, this is going to be rect of x over 10. So that's the response. So the rays going this way give me that. Okay? So that's what that one impulse gives me as my source image. Now let's take a look at the other one. So now this is saying, for here, x naught is equal to 2.5, right? And therefore we have mx naught is equal to 5. Okay? So we know the center of this is now going to be, and this was going from minus 5 to 5. Now the new one has a center, is a rect centered around 5, and it's scaled the same, so it's just going to be a rect function like this. Okay? So we're going to have rect of x minus 5 over 10. Right? Okay. And if the system is linear, which optics is, we'll assume, for now, for this class, we assume that the dimensions of our object are much bigger than the X-ray dimensions, which have very finite wavelengths. So we're not worried about diffraction effects. We're not worried about wave interference or phase. So we can just do a straight summation and just assume that things are additive. So we're going to assume that it does satisfy the additive property of linearity here. Okay. So now my final output then is just a summation of those two. So it's going to look like this. It's going to be here, and then it's going to be like that, and it's going to look like that. Okay, so it's going to be 1 here, 2 here, and 1 there. Okay, so that's what the output would look like. So those two outputs sum together to give my overall output. You guys can't see that, so let me use another color. So this is 1. Oops. It's going to be sum to 2 here, and 1 here. Can you see that now? Okay. So any questions on that? So that's a really simple example of superposition where we have 2 impulses and we're just summing the outputs from those 2 impulses. All right? Okay. So if there's no more questions, let's move on. Okay, space invariance is pretty simple. It's basically if this is the response to this impulse, and now I shift my impulse in space from there to here, okay, so I've shifted my impulse, then my output should shift by exactly the same amount. And that's what's called shift invariance or space invariance. In time, it's called time invariance. And so a typical example of that is if I had a bell and I hit the bell, and you heard the ding ringing of the bell. If it was invariant and I came back tomorrow and hit it exactly the same way, if the system is time invariant, it should just give me exactly the same response. Okay? So that is a space invariant system. Okay. So let's do this one. Is the system linear? We already basically said yeah, because otherwise we couldn't have done superposition. Okay. So now the question I want you guys to think about is this a space invariant system? All right. So let me bring up that poll. Okay. So go ahead and check and see what you think. Is it space invariant or is it not? Okay, this looks like about an 80-20 split. Okay. All right, so 80% say it is space invariant, and 20% say it's not. Both parties are sort of correct, so let's see why. Okay, so let's review this X-ray imaging picture we have here, right? So here, basically, we said here I've shifted by x naught, right? My impulse, right? So that's my impulse, and I'm looking at the impulse response, and the impulse response is shifted by m of x naught. Okay, so if this was strictly speaking a shifted a space invariant system, how much should the shift have been? It should have just been x naught. Okay, but instead I'm getting this extra multiplying factor of m. So unless m is equal to 1, it's not going to be shift invariant. Okay, so when is m equal to 1? When is my object magnification factor equal to 1? Anybody? Yeah, when the object is right next. So if I move this down to here, right, and have my pinhole right next to my detector, then it's strictly shift invariant. Okay, so there is a m value of big M where it is shift invariant. Okay, so we talked about object magnification. So if this is my object T of x, okay, in general, what my image is going to look like is a magnified version of T of x over m. Okay, and m at when the distance between my object and my detector is 1. So when it's 0, then big M equals 1, and so I'm fine, right? There's no object magnification, and the system is shift invariant. Okay, but for everywhere else, it's not so bad. I mean, you basically just have a magnified version of my object, right? So in that sense, as we'll see later on in the X-ray imaging equation, as long as I take that into account, the T of x over m, then I can still sort of treat it almost as shift invariant. At least the mathematics works out. Okay, so and you can think about it that way. You know, if you get a picture, you know, on your computer, in some sense, whether you scale it or not doesn't really matter, right? And so you can always sort of take out that scaling factor in terms of the object magnification just by rescaling it. Okay. So that's sort of a trick question, but it sort of gets at the point of even though it's not strictly shift invariant, you can almost treat it as shift invariant in this case because it's just a simple magnification. All right. Okay, so now let's talk about what happens when you have what are called linear shift invariant systems or LSI system. If it's time, it would be called LTI. Okay, those of you, especially from the EE background, you probably studied this ad nauseum, but for those of other people, it may be a little more newer. So the idea is that, let's say I have an input here, and it's a very simple input, 0, 1, and 2. Okay, then what I'm saying here is my impulse response, if it's linear shift invariant, my impulse response, the shape of it doesn't really matter where the impulse is. It's always going to have this shape. Okay, so therefore I can write the output as just a weighted sum of shifted impulse responses, and that makes my life really easy. I just basically, for this gives me this response. This gives me a shifted version scaled by 2 because this is twice as large. So let's say this is 1, this is 2, and then this is, and let's say this is shifted by 1, so it's at 0, and this is at 2. Okay. So now my output, if I were drawing my output, would just be the sum of all these things. So my output is going to look something like that. Okay. So I have each impulse gives me a response. Each of the responses is a shifted version of the same response, the impulse response, shifted and weighted, and then my output, I just sum them all up. Okay, so that's the intuition. So let's go through this again. So basically we had before, we have this is L of n of this thing, G of 0, delta M, plus G of 1, okay, and now I'm just going to do 2 steps together just because we know linearity applies. So I can factor out the G of 0, and I can also break up the sum. Let's erase that. Okay, so we had exactly the same thing we talked about superposition. Now the only difference is each of these is just going to be a shifted version of my impulse response. So I can write this as g of 0, h of m minus k. In this case, it's just m minus 0, plus g of 1, h of m prime minus 1, plus g of 2, h of m prime minus 2. Okay? And then so the summation is just this. Okay? So this is basically what's called a convolution sum. All right? So basically it's got the weightings, and these are just shifted versions of the same impulse response. Right? And so the clean version is there, and it's saying output is the weighted sum of shifted impulse responses. Okay. So this is now we're going to for continuous functions we use the integral sign. So we replace the summation with the integral, and we also have to add the differential here. But it has the same form. So we're going to have g of I, h of x minus I, g of I, the integral over that. Okay? And so typically the way that's written is we use this symbol to represent convolution. Okay. And an extremely useful fact, which we will use in just a minute, is basically that if I convolve g of x with any shifted Dirac Delta function, then it actually just shifts that function. Okay, and that becomes really useful because basically a lot of times we want to be able to just shift things around in space. We want to know what happens when we move things around in space. And what we do is mathematically we say that operation is just convolution with a shifted Dirac Delta function. Okay, so very useful for shifting. Okay, so those of you who have done convolution before know it can be sort of messy. So we're not going to do too much convolution in this course, but we're going to just do enough very basic so you can do some simple problems. And so I'm going to go over something today, but this week's homework that's going to come out, I will also have the links to the videos that I did last year, which goes into it in much more detail. So for those of you who want a little more supplemental treatment of convolution, that goes through that at basically the same material, but it's slightly slower pace. Okay. So let's do our first example, which is fairly simple, which is simply this. I have my function here, which is rect of x, okay, and I'm convolving it with delta of x minus a quarter plus delta of x plus 3/4. Okay, so this is mathematically what I have is this rect of x convolved with delta of x minus a quarter plus delta of x plus 3/4. Okay. And so basically all this is saying is that this useful fact is this operation just shifts that function to have its origin or the center wherever the Dirac Delta has its center. Okay. So I can just write down the answer by inspection. It's rect of x minus 1/4 plus rect of x plus 3/4. Okay, so that's very simple. And so let's draw what that looks like. So this is going to be a rect that's centered out in 1/4. Okay, and the rect goes 1/2 one way and 1/2 the other way. So it's going to go from minus a quarter to 3/4. So that's going to be this rect. Okay, so that's this rect. All right. Let's use another color for the other rect function. So the other rect function is going to be centered around minus 3/4, right? Because x plus 3/4 equals 0 when x equals minus 3/4. So it's going to be centered around minus 3/4. Okay, it goes 1/2 this way and then 1/2 this way, so it's minus 5/4. So it's going to look like that. Okay, so So that's where that rect goes to. All right. So that's what the solution is. It's just two rect functions shifted and the summation of the two things. Okay. So the answer is basically those two rect functions together. All right. Okay. So that's a very simple one. So you want to get, because this type of operation is going to come in really useful for the later on in the class. This is what we'll mostly focus on because it's just shifting things around. But there is going to be a need to have at least some understanding of slightly more complicated convolution. And this is the most simple one that we're going to do right now. And then when we do X-ray imaging, we'll do a slightly more complicated version of this. So here's the idea, which we'll discuss much more in depth in the supplemental videos, which is basically what this function says is I have to take one of the functions and flip and shift it, right? So this is this is taking h of x, and the shifting is this minus xi, and then the shift. So let's say we have h of xi here, then it's a minus xi, which is a flipping, and then the shifting, we're shifting by x. Okay, we multiply it by g of xi, and then we integrate the product. So I'm just going to go through an example of that. And then what we want to say is what happens if I convolve rect of x convolved with rect of x. Okay, so the question is, what is that output? Okay, and that's going to come in really useful because we're going to imagine what happens. For example, this might be my source function, and this might be my transfer function. I want to be able to see what happens when those two things are convolved together. So let's take an example of that. So what we said is our convolution is going to be g of xi, h of x minus xi d xi, and this is my output. Let's call it y of x. Okay? So that means that each value of x that I want to evaluate, I want to slip and shift it by x, multiply it, and then summation. So let's take a look at that. So this g of xi stays the same. That's the same for all of these guys. Okay? Here I've taken h of 0 minus xi. So that's just a flip. So h of minus, this is basically just h of minus xi. So that's just a flip version of h of xi. Since it's symmetric, it doesn't do anything. So now here's the thing. I want to take this function here and multiply it by this function here. Okay? So basically, wherever this is 1, I multiply it by 1. So the output here is 1. Okay? So this is these two things multiplied by together just give me this as my output. Okay? And so now I take the area. So the area of this is equal to 1. So I would say that y of 0 is equal to 1. Okay? Here I want to figure out the value at y of 1. Okay? So in this case, I have to take x is equal to 1. So it's h of 1 minus xi, which I can draw like this. And if I look at this guy multiplied by this guy, there's no overlap. This ends at a half. This starts at a half. So the overlap here is 0. Okay? So when I integrate it, it's just 0. So I can say y of 1 is equal to 0. All right? Here I'm looking at x equal 0.5. So this is the function h of 0.5 minus xi. So it's basically this function shifted by a half. And so now if I look at these two functions multiplied by together, the only place they overlap is here. Okay? So this is the overlap. When I multiply those two functions together, this is the function I get out. And so this area now is equal to what? It's just a half times 1. So I could say that y at 0.5 is equal to 1/2. Okay? So that's what the convolution does. The good thing is that you end up with, for this class, so this ends up looking something like this. It's 1 here, it's 0 here, and it's just linear function. Okay? And in this class, you're either going to get things that look like triangles, or you're going to end up getting things that look like trapezoids. Okay? And so we can go into that more in some of the office hours, but the idea is that's the limit of convolution we're going to do for this class. Okay? 2D convolution is the same thing, except now we're extending things to 2 dimensions. And 2D convolution, we're not going to ask you to do that by hand because it's really, really messy. Okay, so we're only going to ask you to do 1D convolutions by hand, if at all. And 2D convolution, will you do it, we'll have you do it. That's what you're doing in the MATLAB exercise for this week. You're doing 2D convolution. But since it's a lot more computation, we're letting you do it with the computer. So let's look at an example of this. So here I have, I want to evaluate rect of x comma y. I'm doing a 2-dimensional convolution of that with this function, x plus 1/2 comma y plus delta x y. Okay? So let's look at the first one. So if I take my rect of x, y and convolve it with this, it just shifts it to where the Dirac is. And so that's just at the origin. So that just gives me, so that convolution just gives me rect of x, y. Okay? So that, if I convolve this with that, because it's a Dirac located at the origin, it doesn't do anything to my rect function. Now let's look at this part. We're going to take the rect function and convolve it with this guy here. So this is a delta that's shifted over by 1/2. So that's just going to be rect. It's going to shift my function to 1/2 that way. So it's x plus 1/2 comma y. Okay, so that's all you have to do. If you have Dirac delta functions and you're convolving with some object, it just shifts your object around. And now my output is a summation of those 2 rect functions. Okay, so what it looks like is this. Basically, my first rect function, if I draw the outline, was just this one here. Okay, that's my rect function. Rect of x, y is there. The shifted rect function is just this one, right? And then when I add them together, you're going to notice I get the value here is 1. When they add together, it's 2, and then it's 1. Okay, so that's my object. All right. So it's just sort of trying to introduce you to realizing that these very simple operations that we can think about, starting to add some math to how we actually move things around in space. Okay. And so this is going to be the 2D convolution example that you're going to do with your MATLAB. And essentially, you're going to create this cross. Okay. And then these are different types. These are different Gaussians. Okay. That you're going to create in MATLAB. And you're going to convolve the two and end up with a blurred version of your cross. Okay. So, and as you can see, as this gets blurrier, the cross gets blurrier as well. All right. So that's just to try to introduce you to 2D convolution. All right. Okay. So now, in the last 15 minutes, we're going to finish up and apply this to X-ray imaging, and basically start to sort of capture everything we've talked about. So last time we talked about source magnification and object magnification. Today we had to go back on some sort of mathematical sort of fundamentals to sort of get us up to this place. Now we're going to try to put everything together and say what actually happens if I have a source and I have an object. What is that the image going to look like for any arbitrary source, any arbitrary object? I would like to know what my output looks like. Okay. So as a reminder, in the very simple case, if I have my source here S of x and I have a Dirac located at the origin, I just end up with a magnified version of my source. Okay, so that's what we talked about last time. Okay. The next level of we added was what happens if I shift my pinhole over by x naught. Okay. Then it just said, okay, well you just take your source and then you also shift it over by that big mx naught, and then also you have to scale it as well. Okay. So once again, we saw the shift, and then we saw the scaling. Okay. And so it turns out, and here we're not going to expect you to go through the derivation. I'm just going to tell you what the answer is. The book sort of skips over it too. For those of you who really want to go through it, we can sort of sit down offline, but you're not expected to understand the derivation. I'm just going to tell you what the answer is and give you some insight into how to work with it. So it turns out that that expression, the shift with a shift and a scaling, can be written as a scaled version of my source convolved with a version, with my delta function. This is my transmission function with a magnification factor of m. Okay, so remember my object was 1 over m delta x minus x naught. Okay, so it turns out if I just introduce these m factors here, then I can rewrite this. I can write this mathematically as this convolution. Okay, and so that gives me some insight. It's saying, okay, whatever your object was, you actually need to now essentially, this can actually then be written as a magnified version of my object. Okay, so what it's saying is once you do all the math, you simply need to take a scaled version of your source and convolve it with a magnified version of your object. And that's going to give you your image at the end of the X-ray imaging. Okay, so that's for 1D. For 2D, it's the same thing. I take my object, I magnify it, and then I convolve it with my scaled version of my source. All right? So let's look at an example of that. So now we have this case here where we have my source is equal to rect of x over 10, and my object is equal to rect of x over 10. And the question is, what is my image going to look like? Okay. So the nice thing about X-rays is you sort of guess what the answer might be. Okay. So we're actually going to go through. I'm just going to walk you through how you just guess what the answer would be, and then we're going to see how that comes through with math. All right. I think we have enough time just to sort of sketch out the proof of that. Okay. So let's think about this. Each of these, we can think of this as there's X-rays coming from all these little sources here, right? Right. That extended source can be thought of with lots of little sources, right? Lots of little Dirac Delta functions, each giving off X-rays. So let's imagine how many X-rays can go from, can any X-rays go, so and X-rays can only go through here, right? This is the only place a transmission function is greater than, is not equal to 0. So anything out here gets blocked. Okay, so no X-rays can get through. Okay, so can any X-rays end up here? No, they can't. There's no path for an X-ray to end up here, and there's no path for X-rays to end up here. Okay, so just by looking at it, we can tell how big my image is going to be, because it's going to be the farthest an X-ray can go is from here to here. That's the farthest it can go out this way, right? Okay, and similarly here, this path can go through here. Okay, and only these guys can make it through that path. Someplace here can't actually get to there, right? An X-ray starting here can't actually make it to the end, right? There's no way for it to get through because you can't draw any line that would take it there. Okay? So we know that now as we move in this direction, there's going to be more and more sources that can sort of give rise to X-rays that go there. So we'd imagine that the intensity of my image should increase linearly here, because more and more X-rays, as I move away from that edge, more and more X-rays, so lots of X-rays can make it here, more X-rays can make it here, even more X-rays can make it there. Okay? And then it's going to increase until at some level, for example here, in this regime, like here, in this regime, a lot of the X-rays can make it through, right? So let's say the middle point, all the X-rays can make it through to that point, right? Okay, and similarly, all the X-rays can make it through that path there. Okay, so we're going to imagine. So we know our function has to end up looking something like this. Okay, so there's going to be some region where all the X-rays make it through. Okay, so there's going to be some flat region where you can imagine if I pick any point here, if I pick a point here, then I can have paths, all the X-rays can make it through to that path, okay, to that location, all right? And then on the sides here, that represents region where only some of the X-rays can make it through. And as I move farther and farther out, less and less X-rays can make it through, okay? So in general, anytime you have this sort of situation, you're going to end up with something like that, okay? So let's look at this. So for this case, we have little m equals 1 and big M equals 2. Okay? So let's just look at that. So we had our S of x was equal to rect of x over 10. So that doesn't change. Little m is equal to 1, right? We had our transmission function was equal to rect of x over 10. So that does change because now we need t of x over big M, right? So that's going to be equal to rect of x over 20. Okay. So let's just walk through what that might look like. So this is rect of x over 20. Okay, so let's just draw that. So we've got, this goes from -5 to 5 and has a value of 1. Okay. The other one goes from -10 to 10 and has a value of 1 as well. Okay. And now we want to convolve those two. So let's look at, and we know our answer is going to look something like this, right? We just and this is the nice thing about imaging is you can sort of imagine what the answer would be, and then you can sort of now just fill in. Now I just have to figure out how tall is this and where are these breakpoints? You know, what are these points here and how tall is it? Okay, that's all I have to do. So really, there's only 3 numbers. I need to know this number, and this number here. Okay, so now we can just go through and say, okay, as long as I can figure out what those numbers are, I'm all set. All right, so let's figure out how you would sort of walk through where those numbers are. So here, when we do the convolution, remember we're going to multiply these two functions by each other, right? So right in the middle, here, I don't have to shift anything. So I can imagine if I multiply these two functions by each other, so let's say at x equals 0, if I multiply, then these two functions are just simply going to give me the rect function back, right? Okay, because this overlap here, if I imagine multiplying the functions there, since they're both equal to 1, 1 times 1 is 1, so the multiplication of those two functions just gives me that. So what is the area of this? So this has height of 1, width of 10. So what's the area? It's 10. So we've already figured this out. That's 10. Okay, so that was easy, right? Okay, so now let's think about where is this point here? Okay, so now the question is how far can I shift this guy that way before it no longer overlaps with the top one? Okay, so I think about this. This is at -10. I've got to move this edge all the way over to here. So I've got to shift this all the way over to here before it no longer overlaps, right? So that shift going from -10 to 5 is how long? It's 15. So this is at 15, and this is at -15. Okay? And then similarly, you can imagine taking this. I could do lots of shifts here, and it's still going to overlap completely with this top one. At what point does it stop overlapping completely? So that's when this edge gets to, let's see, once this edge gets to here, right? Let's say I'm here, right? So this still has complete overlap, but once I move past this edge, it's not going to overlap anymore completely with this one, right? So going from here to here is a distance of what? 5, right? Okay? So that's my answer. It's not to scale, but that's essentially what it is. So it's just showing mathematically what we sort of thought about physically and intuitively actually matches the math. That there's going to be some region where all the X-rays get through, and then as I go off that region, less and less X-rays get through until it falls to 0. Okay? So that's basically what happens with all X-ray imaging is essentially you're going to have this region where it's pretty good in the center, and then at the edges things start blurring out. All right? And that's shown here where we have this penumbra, which we've talked about before, okay? Where you have this very solid thing, but then at the edges it sort of blurs out. Okay? And so that's what we want to minimize. And how do we minimize that? Once again, we put our object right next to the film. Okay? So that's going to minimize that penumbra. Okay? Because that's going to make the source, it's going to make this guy, this S of x of m, go to the delta function. right? And that's what we want. We want to make that become a delta function, because then my object convolved with a delta function is just my object. Okay, so that's what we're looking for, and that's sort of trying to introduce how we start using math to understand physical systems. Okay, so in the last few minutes, I'm just going to. So this is sort of the this is the equation that we have. Okay, in 2D, and what we've said is we've ignored obliquity factors, so we're just going to add a few other factors in that the book talks about, just so you sort of have, you understand how what we've derived is linked to what's the equations in the book. So when you're reading it, you have a little more context. So there's a couple of factors. One is the inverse square law, which is basically saying that the intensity falls off as the distance squared. Okay, and so you imagine the surface area of a sphere, right? The volume is proportional to the radius squared. Surface area is proportional to the distance squared. So we're taking some intensity and normalizing it by the surface area of a sphere. So that gives you this 4 pi d squared. Okay, and it turns out that you can write this in these different forms, where you have, for example, your intensity times the cosine squared theta divided by 4 pi d squared. Okay, where basically the idea is, if this is my object, this is my source, my detector, the angle theta is defined as such, and then d is this distance and r is that distance. Okay, so that's all just geometry that's being introduced to express how much the intensity falls off the further away you get away from the source. So that's all that is. The other thing is what's called the obliquity factor, which is basically the idea that, you know, the source drop off was assuming spherical wavefronts, right? That things are falling off with a sphere. So it's giving you the answer along the sphere, but really what we use is a flat detector, okay, in general, okay? And so there is an additional cosine theta factor that accounts for the difference between this sphere and then this flat thing. And so that ratio of the surface areas, that cosine theta ratio, is what this obliquity factor takes into account, okay? So all that means is that at the end of the day, you actually have this additional cosine cube theta term that you have to, the intensity falls off along a flat panel with that cosine cube theta term. But it turns out it's pretty small. So this is an example from the book. If we do a chest x-ray at 2 yards with a 14 by 17 inch film, what's the smallest this cosine cube theta gets to be? And it turns out it's like 0.966. So there's really only like a 4% drop off in intensity across a big film. So in general, you can pretty much ignore it. It's not going to be the main factor, but it's just good to know for completeness. So all we're going to do now is we've already done this part. This is the part we did before, and now we're just adding on these factors. And so the final thing, that's equation 5.28 in the book, is simply, this was all the stuff we did with the convolution and the magnification, and then you're just adding on this additional correction term here. Okay, so there's this cosine cube theta term, which tells you how things fall off sort of as you're varying across the film, and then there's this d squared term that basically is the attenuation as you move the source away from the film. Okay, that's just things are spreading out farther the farther you move out. All right, so that is the X-ray imaging equation. The main point to get across is you're always going to have your object convolved with your source image. Okay, and so the ideal is to make this as close to a delta function as possible. Okay, and you do that by making, you know, m going to 0 and m equals 1 by putting the object right next to your film. And obviously that's not always possible, so as you move away, then you start introducing these other factors, some blurring, some magnification. Okay, but the object is always to try to minimize that, because even if you didn't care about the magnification, you definitely want to minimize the blurring of your object. Right? And that's going to be the same for CT and MRI. We're always trying to get the best resolution possible. You want to see your object. You don't want to have it blurred out by your system. Okay, so that actually brings us to the end of today's lecture. So I'll post this on video later today. And I'll stay here for office hours if you have any questions about either the lecture or the homework assignment. And then Ashish will be posting an email about the TA office hours And probably good to remind people about the MATLAB as well. Okay, thanks.